In March 1944, at the German airfield of Rechlin in Mecklenburg, the Luftwaffe's technical intelligence branch was deeply engaged in studying captured Allied aircraft. Rechlin served as the Reich's central flight test and evaluation facility, where engineers and test pilots analyzed enemy machines to identify strengths that were shifting the air war over Europe. What they uncovered in early spring that year forced a major reassessment of American industrial output and long-range fighter capability. On 6 March 1944, a relatively intact P-51 Mustang arrived at Rechlin by rail after being recovered from a crash near Brandenburg. The aircraft had been shot down 2 days earlier during one of the first American escort missions to Berlin. Although the pilot did not survive, the fighter itself remained largely undamaged, offering German technicians their most complete example yet of the aircraft that was quickly altering the balance of power in the skies over Germany. Initial inspection was supervised by Hermann von der Bombach, an officer involved in aircraft development who would later hold senior command positions. Inside the cockpit, the pilot's navigation materials revealed a planned route from Debden Airfield in England to Berlin and back. An astonishing round-trip distance that exceeded what German planners believed single-engine fighters could achieve while still fighting effectively. Until then, German intelligence had assumed that American escort fighters lacked the range to accompany bombers all the way to Berlin. The one-way distance from England to the German capital was roughly 560 miles, and earlier evaluations of captured P-47 Thunderbolts and P-38 Lightnings suggested that even with external tanks, such aircraft would have to turn back before reaching deep into German airspace. Events on 4 and 6 March 1944 overturned that assumption. On 4 March, P-51 Mustangs of the U.S. 4th Fighter Group flew their first Berlin escort after recently converting from P-47 seconds. Weather and coordination issues limited the operation, and only a small number of bombers reached the target. Nevertheless, the implications were unmistakable. American single-engine fighters had reached Berlin, engaged German aircraft, and returned to England. 2 days later, on 6 March, roughly 66 American bombers struck Berlin in daylight. More than 150 P-51 Mustangs, along with P-38 seconds and P-47 seconds, escorted the formation. These fighters battled Luftwaffe interceptors over the German capital and remained with the bombers for the return journey. This demonstrated that the Americans had solved the long-range escort problem, not by chance but through systematic capability. General Major Adolf Galland, General der Jagdflieger and one of Germany's most accomplished fighter aces, flew operational sorties during this period despite his administrative duties. Encountering P-51 formations over Germany, he immediately grasped the significance. In his reports, Galland noted that the American fighters fought aggressively over Berlin at full combat power and showed no sign of conserving fuel. They were not operating at the edge of their endurance, they appeared to have reserves. This observation directly contradicted existing Luftwaffe assessments. Galland also emphasized the Mustang's performance at altitude. Above roughly 20,000 feet, the P-51 outperformed both the Messerschmitt Bf 109 and the Focke-Wulf W190 in speed and maneuverability. At Rechlin, technical teams set out to determine how the Americans had achieved such range. Measurements of the P-51B's fuel system revealed 2 wing tanks holding 92 gallons each, plus an 85-gallon fuselage tank behind the cockpit. A relatively recent addition designed to extend operational range. Total internal capacity amounted to 269 gallons. The Packard-built Merlin engine, a licensed version of the Rolls-Royce design, consumed fuel at varying rates depending on power settings. Around 60 gallons per hour at economical cruise and up to 75 gallons per hour at standard cruise. Using these figures, German engineers calculated that the aircraft could remain airborne for about 3.8 hours on internal fuel alone. At a cruising speed near 300 miles per hour, this suggested a theoretical maximum range of roughly 1,140 miles, barely enough for a round trip from England to Berlin, and without allowing for extended combat. Yet combat reports describe dogfights over Berlin lasting 15 to 20 minutes or more, with fuel consumption during such engagements exceeding 100 gallons per hour. By those calculations, the aircraft should not have been able to return. The discrepancy forced a closer look at the Mustang structure. Under each wing were reinforced attachment points equipped with fuel connections, clearly intended for external tanks. Drop tanks themselves were nothing new. German fighters had used them since the Battle of Britain. The Bf-109 and W-190 both carried external fuel containers to extend range, discarding them before combat to regain performance. The key issue was not whether the Americans employed drop tanks, but how large those tanks were and how they could be produced in sufficient numbers to support sustained operations. German intelligence began searching for jettisoned tanks from the March missions, plotting likely release zones based on reports from Luftwaffe pilots. Typically, such tanks would be dropped when enemy fighters appeared, since the added weight and drag reduced maneuverability and speed. The investigation into these external fuel tanks quickly became central to understanding how American fighters had achieved their unprecedented reach over Germany. Search parties made up of Wehrmacht personnel and Hitler Youth volunteers combed the rural areas northeast of Berlin, hoping to locate remnants from recent air engagements. Within a few days, wreckage began to surface in fields and wooded areas. Most of what they found had been shattered on impact or damaged during descent. However, 2 examples were recovered in comparatively good condition after landing in soft earth and winter wheat that had cushioned their fall. These intact finds quickly drew the attention of German technical staff. The captured external fuel tanks provided new insight into American industrial practices. Each tank was cylindrical, roughly 108 inches long and about 22 inches across at its widest point. Estimates suggested a capacity of around 108 US gallons, about 400 liters per tank. When mounted in pairs, they added roughly 216 gallons of fuel, bringing the P-51 Mustang's total capacity to approximately 485 gallons. At cruising power, this allowed for endurance approaching 6.7 hours and a range beyond 2,000 miles, more than enough for missions to Berlin with reserves for combat. The arithmetic behind the Mustang's extended reach was now clear. Yet what truly intrigued German engineers was not how much fuel the tanks held, but how they were made. At first glance, the exterior finish appeared metallic, coated in silver paint, but touch revealed the surface unlike aluminum or steel. When technicians carefully scraped away paint near the tail section, they discovered layered sheets of thick paper, each roughly half a millimeter in thickness, pressed and bonded together with a resin adhesive. The nose and tail sections had been formed from overlapping segments shaped much like papier-mâché, leaving faint ridges where pieces met. The central cylindrical body, by contrast, was wrapped smoothly in continuous laminated layers. Brass fittings were precisely machined and well sealed, and inspection through the filler opening showed an interior lined with a cellulose-based lacquer intended to protect against aviation fuel. Material specialists were called in for closer examination. The paper was identified as a chemically pulped kraft paper known for strong cellulose fibers similar to that used in heavy industrial packaging. The bonding agent proved to be a resorcinol-formaldehyde resin, a heat-cured polymer capable of producing joints stronger than the paper itself. At least a dozen layers had been laminated together, oriented to maximize strength from different directions. Inside, wooden anti-slosh baffles prevented fuel movement during flight maneuvers. The entire design suggested a standardized process optimized for rapid, large-scale production. An empty tank weighed around 80 pounds, comparable to, and sometimes heavier than, smaller metal tanks, so weight savings were modest. The real advantage lay elsewhere. German engineers quickly grasped the implications. These tanks were built from non-strategic materials, paper and wood-derived resins rather than scarce metals. Their manufacture required no specialized metalworking machinery, welding, or highly trained labor. Facilities that produce packaging or paper goods could be adapted with minimal changes. Given the vast number of such factories in the United States, even a small diversion of capacity could generate thousands of tanks weekly. The recovered examples bore no serial numbers or identifying marks, reinforcing the impression that they were mass-produced, disposable items. Intelligence personnel began assessing American paper production. Before the war, U.S. output stood at roughly 12 million tons annually, and wartime mobilization had increased it further. Redirecting just a fraction of that capacity, perhaps 1%, could theoretically produce well over 100,000 tanks per month, far beyond the needs of Mustang operations. The limiting factors would likely be assembly capacity and labor, yet the manufacturing process seemed suited to semi-skilled workers after brief training. To German planners, the scale of resource efficiency and industrial flexibility behind these tanks was striking. Further examination revealed another key detail: the tanks were intended for single use. Although the resin bonds were strong when cured, extended exposure to aviation gasoline gradually degraded the adhesive. This confirmed that the tanks were designed to be expendable components, produced in large quantities, used once, and discarded, an approach reflecting the industrial depth and logistical strategy of the American war effort. Interrogations of downed U.S. airmen and analysis of captured material revealed an unusual feature of certain American external fuel tanks. These tanks, made primarily from treated paper, could not remain filled for long periods without seeping fuel. They had to be loaded shortly before takeoff and were intended for only a brief service life. In practice, this limitation caused little difficulty. Fighter aircraft were fueled as part of standard pre-flight routines. The auxiliary tanks were consumed during a mission lasting only a few hours, and then they were discarded. Because they were meant to be thrown away after use, there was no requirement to retrieve, service, or inspect them. Their expendable nature actually simplified supply chains. German evaluators also recorded a straightforward visual coding system. The paper tanks carried a silver coating, while conventional metal tanks used by U.S. units were finished in gray. Ground crews could therefore distinguish them quickly during refueling. The reflective silver surface had an additional benefit. It reduced heat absorption from sunlight, helping to limit fuel evaporation and pressure buildup at altitude. The overall concept showed careful engineering aimed at large-scale production and practical field handling. By the end of March 1944, German intelligence had traced the origin of these disposable tanks back to Britain. In 1943, the Air Ministry in London had initiated development of fuel containers made from resin-treated paper to conserve scarce metals, especially aluminum. The Bowater Scott Company, drawing on its experience in paper processing, established the manufacturing method. Royal Air Force fighter units began using the tanks in late 1943, and American forces soon followed. Factories in both the United Kingdom and the United States turned out large numbers for U.S. Army Air Force's fighter groups. What began as a British response to material shortages was ultimately amplified by the industrial scale of American production. The implications reached beyond the tanks themselves. German technical specialists expanded their review to other captured U.S. equipment, searching for patterns in manufacturing practice. Their findings were consistent. Individual American components were not always superior in performance. German optics frequently offered clearer images. Small arms from Germany often featured more intricate engineering, and certain aspects of German armor metallurgy were highly advanced. Yet American equipment displayed a different strength. It was easier to manufacture, more standardized, generally more reliable in service, and produced in far greater numbers. The design philosophy emphasized ease of production rather than absolute refinement. Parts were conceived from the beginning to be made in quantity by workers with limited specialized training, using uniform tools and gauges. Interchangeable components eliminated the need for custom fitting. Assembly line organization shortened build times and increased throughput. This contrasted sharply with German practice. Many German weapons and vehicles were crafted with exceptional precision, often assembled or finished by highly trained specialists. A German tank or aircraft engine could represent the pinnacle of engineering craftsmanship, but producing each unit required time, skilled labor, and specialized machinery. Output was therefore limited by the availability of expert workers and precision equipment. In effect, Germany produced highly refined individual systems, while the United States manufactured sufficient systems in overwhelming volume. In a war of industry, sheer quantity proved decisive. The production history of the P-51 Mustang illustrates the difference. North American aviation began work on the aircraft in response to a British request in 1940. The prototype, designated NA-73X, was completed only 117 days after the contract was issued, an exceptionally rapid development cycle for the era. Its first flight took place on 26 October 1940. By 1944, Mustang production was running at two major plants. The Inglewood, California facility averaged roughly 364 aircraft per month at peak, while the Dallas plant added further output. Together, they produced about 574 Mustangs monthly during 1944, with numbers continuing to rise. The highest monthly total reached 881 aircraft in January 1945. Each P-51 incorporated around 15,000 separate components supplied by hundreds of subcontractors across the United States. Packard-built Merlin engines were assembled in Detroit at rates exceeding 300 per month. Final assembly of a P-51D required approximately 22,000 labor hours, yet the flowline system meant completed fighters emerged from the factory every few hours. At maximum efficiency, one aircraft left the line roughly every 2 hours. No German aircraft program matched this scale. In early 1944, Messerschmitt and Focke-Wulf together produced about 600 fighters per month. Even under emergency measures and with forced labor, German output lagged behind. The disparity in resources underscored the gap. U.S. aluminum production alone reached about 1.25 million tons in 1944, roughly 2.5 billion pounds in a single year. U.S. wartime output represented a dramatic leap from the roughly 164,000 tons of aluminum produced in 1939. German production, by comparison, reached only about 250,000 tons annually at its peak, and then began to fall as bombing campaigns damaged factories and key raw materials such as bauxite became harder to obtain. Overall, American industry possessed roughly 10 times the aluminum capacity available to Germany. For that reason, the decision to build auxiliary fuel tanks from paper rather than metal was not born of necessity. The United States had enough aluminum to manufacture all such tanks conventionally if it had chosen to do so. Paper construction was adopted because it lowered costs, reduced the need for specialized machinery, conserved strategic metals for other priorities, and allowed rapid production by workers with less training. It was an exercise in efficiency, not a sign of shortage. News of this approach had a notable psychological effect within German aviation circles. The disposable paper fuel tank came to symbolize the vast industrial advantage enjoyed by the United States and the widening resource gap between the two sides. Captured examples were displayed during technical briefings for Luftwaffe personnel. Pilots converting to fighter units were shown the tanks and asked to consider what they meant for future air combat. The implication was unmistakable. American fighters could now accompany bomber formations anywhere over Germany. The earlier defensive tactic waiting for escort fighters to run low on fuel and withdraw no longer applied. German interceptors would have to fight their way through escorting fighters to reach the bombers, a process that would steadily drain aircraft and trained crews. Adolf Galland repeatedly outlined these realities in meetings with senior Luftwaffe leaders in the spring of 1944. He stressed that at altitudes above 20,000 feet, the P-51 Mustang held a clear advantage. It outpaced the Bf-109 at high altitude and maneuvered more effectively than the F-190. With long-range tanks, it could protect bomber formations throughout entire missions. German fighters could no longer attack unescorted bombers. Every interception now required engagement with Allied escorts first. Losses began to rise accordingly. In January 1944, the Luftwaffe lost around 90 fighters while claiming about 150 Allied aircraft. By February, German losses had climbed to roughly 160 aircraft against about 230 Allied losses. The pattern pointed to an unsustainable trajectory. The United States and Britain could replace aircraft and crews faster than Germany could destroy them. By the summer of 1944, the full impact of long-range escort fighters became evident. The U.S. Stats 8th Air Force launched deep raids into Germany almost daily when weather allowed, with Mustangs accompanying bombers from England to targets deep inside the Reich and back again. German fighter losses reached severe levels. In June alone, roughly 350 daytime fighters were lost defending German airspace. July saw more than 350 single-engine fighters destroyed in the Western Theater, representing over 30% attrition in a single month. August brought comparable figures, with losses approaching 36%. At such rates, experienced pilots were being killed faster than replacements could be trained. New German pilots often arrived with perhaps 150 flight hours, compared with 300 or more for American counterparts, and some had only about 30 hours in their specific aircraft before entering combat. The gap in experience, combined with numerical inferiority and constant escort coverage, made daylight operations increasingly hazardous for German forces. Throughout this period, Galland submitted repeated evaluations to Hitler and senior Wehrmacht officials. In a report from September 1944, he described the situation plainly: the Luftwaffe could not prevail in the air war. Germany lacked sufficient resources, fuel, aircraft, and trained personnel to challenge Allied air dominance. American production capacity far exceeded what German forces could offset through combat. The only realistic course, he argued, was to conserve remaining strength for defending essential targets and hope for a political resolution before total collapse. Meanwhile, the paper fuel tanks continued to fall across Germany through late 1944 and into 1945, a constant reminder of the industrial imbalance shaping the conflict. German civilians gradually became familiar with the long, metallic cylinders scattered across farmland and wooded areas. At first, some people mistook them for unexploded bombs, triggering alarm in nearby communities. Military authorities later clarified through civil defense channels that these objects were not weapons at all, but discarded external fuel tanks from Allied aircraft. Leaflets and briefings explained that the shiny cylinders dropping from high-flying formations were empty and posed no danger. Even so, their presence affected morale. Civilian reports noted how the sky was often filled with contrails from vast numbers of enemy planes, whose pilots casually jettisoned expendable tanks. This spectacle underscored a painful contrast. The Allies could afford to discard materials while Germany struggled to conserve every liter of fuel and every kilogram of aluminum. By 1944, German technical intelligence units continued examining captured American equipment, but their emphasis shifted. Instead of focusing on how to match Allied capabilities, they increasingly documented the widening industrial gap. From a purely technical standpoint, Germany could have produced similar disposable tanks made from paper and resin. The country possessed the necessary chemical expertise and industrial base to manufacture the required materials. In practice, however, such production was unrealistic. Chemical plants were already stretched to supply synthetic rubber, explosives, and other essential war goods. Paper mills were fully occupied with military needs such as maps, documentation, and packaging. Above all, the Luftwaffe had little use for extended-range tanks by late 1944. Severe fuel shortages meant that many aircraft remained grounded, and training flights for new pilots were drastically reduced. Combat missions were constrained not by the number of available planes but by the scarcity of fuel. Extending range offered little value when even local defensive sorties were difficult to sustain. This created a bitter irony for German planners. At the moment when American engineers had solved their range limitations with lightweight expendable tanks, German fighters were immobilized by lack of fuel. The two sides faced fundamentally different realities. The United States possessed abundant aircraft, fuel, pilots, aluminum, and industrial output. Germany, by contrast, fought under conditions of acute shortage against an opponent whose production capacity seemed limitless. By January 1945, the strategic outcome of the war was no longer in doubt. Soviet forces were advancing toward Berlin from the east, while Western Allied armies pushed forward after recovering from the Ardennes offensive. The Luftwaffe could only mount sporadic resistance, hampered by fuel shortages and mounting pilot losses. Technical teams at Rechlin continued to analyze captured Allied technology, but their work had become largely academic. Reports were compiled for record-keeping rather than for practical wartime application. A comprehensive assessment of the P-51 Mustang and its drop tanks was completed in late January 1945. It examined the aircraft's range, the design and materials of its external tanks, estimated production figures, and the operational consequences of their use. The conclusion was clear. American fighters equipped with disposable tanks made from non-critical materials had made daylight bombing over Germany extremely difficult to counter. Germany lacked the industrial strength to match American output, the fuel reserves to sustain large-scale air operations, and the trained pilots needed to replace losses. The report was archived within the Reich Air Ministry. Whether top leadership ever reviewed it remains uncertain. By that stage, battlefield realities had already confirmed its findings. The Luftwaffe, dominant over Europe in 1940, had been reduced by early 1945 to occasional desperate sorties. Precious fuel was conserved for missions that could not alter the overall situation. American fighters operated freely over German territory, escorting bombers and attacking targets at will. Each discarded fuel tank falling to the ground symbolized the industrial imbalance that had decided the air war. In June 1944, an exhibition at Rechlin displayed captured Allied aircraft for Luftwaffe personnel. Among them were P-51 Mustangs, B-17 and B-24 bombers, P-38 Lightnings, Lancasters, Mosquitoes, Typhoons, and several Spitfire variants. Thousands of pilots and ground crew examined these machines firsthand. The disposable fuel tanks were prominently displayed with diagrams explaining their construction and the extended range they enabled. The exhibition served both as an instructional display and a stark reminder of the scale and quality of Allied production. Kilogram 200, the Luftwaffe unit tasked with special operations including flying captured enemy aircraft, operated several P-51 seconds during 1944. Test pilots evaluated their performance in flight. Reports consistently praised the Mustang's cockpit visibility, especially in the later P-51D with its bubble canopy. The aircraft handled smoothly, responded well to controls, and performed strongly at high altitude. Its Merlin engine delivered reliable power, and its range stood out above all. With full internal fuel and external tanks, the Mustang could remain airborne for more than 6 hours, far beyond the endurance of most German single-engine fighters. Insights gained from testing and analysis influenced German defensive tactics during the war's final phase. Recognizing that American fighters could escort bombers throughout their entire missions, Luftwaffe controllers attempted to mass their remaining forces at selected points in hopes of achieving temporary local superiority. But by then, the broader industrial and logistical imbalance had already determined the outcome. Coordinating interceptions against Allied bombing raids required precise timing and organization. German fighter groups were scattered across different bases and had to converge at specific points in the sky to form units strong enough to challenge the heavily protected bomber formations. In practice, this was difficult to achieve. Limited fuel supplies, disrupted communications, and the rapid pace of Allied operations frequently prevented German squadrons from concentrating their forces effectively. Even when they managed to position themselves advantageously, the presence of long-range P-51 escort fighters turned attacks into costly engagements. The strategic reality of the air war had shifted dramatically. In 1943, American bomber formations that lacked sufficient escort had endured severe losses. By the middle of 1944, the situation was reversed. German fighters attempting to reach the bombers were the ones suffering devastating attrition. Among the more unusual artifacts of this period were the disposable paper drop tanks used by American fighters. After the war, intact examples became rare. Most were destroyed when they hit the ground, and many others were intentionally crushed by Allied personnel to keep them from being reused. Because these tanks were designed to be expendable, they were not seen as valuable objects at the time. Only a small number survived, eventually becoming museum pieces and technical curiosities. Several are preserved today in institutions such as the National Air and Space Museum in Washington, where they are displayed alongside the P-51 Mustangs that carried them. Museum notes typically describe their construction layers of treated craft paper bonded with phenolic resin, the companies that produced them, and their fuel capacity of roughly 108 US gallons. What those displays often omit is the reaction they provoked among German engineers who examined captured examples during the war. Technical teams spent considerable time studying the tanks, calculating their implications, and drawing conclusions about Allied manufacturing power. The psychological effect of these simple devices was significant. The drop tanks themselves were not technologically advanced. They were intentionally simplified and built from materials that were not in short supply. Yet this simplicity conveyed a powerful message. The Allied war economy was so vast that designers could prioritize ease of production over durability or reuse. Fuel tanks could be made from paper not because of scarcity, but because it was the most efficient way to build them in enormous numbers. The underlying signal was unmistakable. Resources, industrial capacity, and fuel supplies were abundant enough to allow such choices. German technical personnel quickly grasped what this meant. They were not confronting an opponent forced to improvise with substitutes. They were facing an industrial system so well supplied that it could choose simpler materials purely for efficiency. Post-war interviews with Luftwaffe officers and engineers repeatedly highlighted this realization. Many pointed to early 1944 as the moment when the broader outcome of the conflict became clear. The appearance of long-range Allied fighters over targets deep inside Germany, including Berlin, marked a decisive change in the balance of power. Hermann Göring, questioned after the war, acknowledged that the arrival of these escort fighters severely undermined German defensive planning and played a major role in the eventual defeat of Germany in the air war. Captured P-51 aircraft and their associated equipment also provided lessons that extended beyond the war itself. German engineers who later worked with Allied intelligence organizations or emigrated to the United States carried with them insights into American production techniques and design philosophy. Their later contributions reflected an emphasis on standardization, interchangeable components, and designs optimized for large-scale manufacturing. The paper drop tank became a frequently cited example in engineering education and military studies, illustrating how efficient use of materials and mass production could deliver strategic advantages. The P-51 Mustang itself remained in service long after World War II ended. It saw significant action during the Korean War, primarily in ground attack and close support missions. The same long range that had made it an effective escort fighter over Europe proved valuable in the Korean theater as well. Some air forces continued to operate Mustangs into the early 1982s, demonstrating the durability of the aircraft's original design. More than 15,000 units were built during and shortly after the war, making it one of the most widely produced American fighters of its time. Today, over 100 remain airworthy in private collections and museums. When one of these aircraft takes to the sky, often still bearing the markings of wartime units, it serves as a reminder of its role in securing Allied air superiority beyond their operational use. The Mustang and its disposable fuel tanks symbolize a broader lesson about modern warfare. Their significance lies not only in tactics or technology, but in industrial capacity. The Second World War ultimately demonstrated that the ability to manufacture equipment, vehicles, and supplies on a massive scale and to replace losses quickly could determine the outcome of a global conflict as decisively as events on the battlefield itself. During the Second World War, the United States organized an industrial expansion unlike anything previously seen. By the height of production in 1943 to 1944, American factories were turning out more than 50,000 aircraft annually, launching several ships every day, and manufacturing ammunition by the billions. This vast output equipped not only U.S. forces but also delivered enormous quantities of material to Britain, the Soviet Union, and other Allied nations through the Lend-Lease program. Germany, despite its strong engineering tradition and substantial industry, was unable to equal this level of production. Several factors contributed: a comparatively smaller industrial base, the impact of Allied bombing on factories and infrastructure, shrinking access to raw materials as territory was lost, internal competition for resources, and organizational inefficiencies. Above all, Germany faced a coalition whose combined industrial strength far exceeded its own. Once American industry was fully mobilized by 1942 to 1943, the long-term defeat of the Axis became increasingly unavoidable. Even small objects illustrated this imbalance. Paper fuel drop tanks scattered across Germany in 1944 to 1945 symbolized a war shaped by manufacturing capacity. Their simplicity and abundance reflected the overwhelming scale of Allied production in a way that required little interpretation. Throughout the conflict, German technical intelligence units carefully studied captured Allied equipment. Testing centers such as Rechlin conducted performance trials, materials analysis, and engineering evaluations, preserving detailed records that still offer historians valuable insights. German specialists usually judged American aircraft, vehicles, and weapons with technical accuracy. Where their assessments fell short was in grasping the implications of American mass production. One P-51 Mustang was an excellent fighter. Thousands of them ensured air dominance that no tactical brilliance could counter. The episode of German engineers examining paper drop tanks in early 1944 illustrates a broader truth about industrialized warfare. In contests between modern economies, the ability to manufacture quickly and in great volume becomes as decisive as battlefield skill. Nations capable of sustaining weapons output, maintaining supply lines under pressure, replacing losses, and exceeding an opponent's production gain advantages that strategy alone cannot offset. Lessons drawn from Germany and Japan's defeat shaped military planning throughout the Cold War and continue to influence strategic thinking today. The first Berlin missions in March 1944, escorted by single-engine fighters, marked a turning point in the European air campaign. From then on, American bombers could reach any target in Germany with fighter protection. Losses remained serious but manageable, allowing a sustained bombing offensive. Key industries, synthetic fuel plants, ball bearing works, aircraft factories, and transport networks were struck repeatedly. Combined with Soviet advances from the east and Allied pushes from the west and south, this pressure led to Germany's collapse roughly 14 months after P-51 fighters first accompanied bombers to Berlin. Paper drop tanks remained in widespread use during the final phase of the war. Production continued into 1945 with thousands made each month. They extended the range of P-51 Mustangs, P-47 Thunderbolts, and P-38 Lightnings, and were also employed by British Mustang units on long-distance missions over occupied Europe. Their inexpensive construction conserved strategic metals while enabling long-range operations. This careful allocation of resources, prioritizing efficiency and practicality, typified the broader Allied industrial approach. Modern historians examining the air war over Europe point to many causes for Allied victory, but the decisive role of industrial capacity stands at the center. In a conflict defined by factories as much as by front lines, the side able to build more, faster, and more efficiently ultimately held the advantage. Allied victory in the air over Europe resulted from a combination of advantages rather than a single breakthrough. They fielded more aircraft and better trained pilots, held key technological leads in radar and communications, and carried out a sustained bombing campaign that steadily damaged German industry, transportation, and fuel production. Over time, continuous combat drained German resources faster than they could be replenished. Within this broader context, the P-51 Mustang and its disposable drop tanks, some of them made from treated paper, played an important but not solitary role. Air superiority emerged from the coordinated use of multiple fighter types, bomber formations, industrial output, pilot training systems, intelligence work, tactical development, and a long-term commitment of material resources. The paper drop tank is often remembered because it illustrates the industrial and logistical strengths behind Allied success. Technical intelligence units in Germany carefully examined captured equipment and recorded their findings with the meticulous attention typical of German engineering practice. Reports preserved in archives, including those now held in the Bundesarchive, list measurements, performance figures, manufacturing techniques, and estimated production capacity. With access to both German and American records, historians can see that these analyses were generally correct. German specialists recognized the scale and effectiveness of American production. What they lacked was any realistic way to counter it. Knowing an opponent's strength does not eliminate the structural imbalance created by differences in industry and resources. The significance of the paper drop tank extends beyond its wartime function. It demonstrates that an effective solution does not have to be complex or elegant. A fuel tank made from laminated paper, designed for one-time use and built from non-critical materials, met the operational need of extending fighter range. It did not aim for technical perfection. It aimed to work reliably and to be produced in large numbers quickly. This philosophy, prioritizing adequacy, manufacturability, and speed over refinement, became a core idea in modern systems engineering. The most valuable design is often the one that fulfills requirements within available time, materials, and industrial capacity. The aircraft that carried many of these tanks, the P-51 Mustang, became one of the most effective fighters of the Second World War. Its success stemmed from a combination of factors: a streamlined airframe developed by North American Aviation under Edgar Schmood, the dependable and powerful Merlin engine, an additional fuselage fuel tank that increased range, and the widespread availability of external tanks that extended operational reach to well over 800 miles. No single feature made the Mustang decisive. Its effectiveness came from the integration of all these elements and the ability of American industry to produce them in quantity. By early 1944, German engineers evaluating captured Allied equipment at facilities such as Rechlin saw more than technical specifications. They saw evidence of a widening strategic gap. The disposable tanks revealed that the United States could manufacture large numbers of specialized components using abundant materials. American engineering tended to favor practical, scalable answers over intricate but hard-to-produce designs. The Allies, with greater access to raw materials and industrial capacity, could optimize for efficiency instead of resorting to emergency substitutions. These realizations, arriving in March 1944 while the war's final outcome was not yet officially settled but increasingly predictable, gave German technical staff a clear picture of the situation they faced. However, this awareness could not alter the larger course of the conflict. Decisions made at industrial and political levels outweighed anything engineers at testing stations could change. Still, the scene of specialists studying simple paper cylinders, calculating fuel volumes, and considering their implications for bomber escort missions highlights how production capacity shapes modern warfare. The war in Europe ended in May 1945. The sustained bombing campaign, made more effective by long-range fighter escorts such as the P-51, had severely disrupted German manufacturing, damaged transport systems, and contributed to critical fuel shortages. The Luftwaffe was reduced to a limited defensive force. These outcomes resulted from many interconnected developments over several years, but the ability to protect bombers deep into German territory, made possible in part by extended range fighters carrying external tanks, was among the decisive factors. Only a few of the paper drop tanks survived the conflict. Some entered museum collections, while most were discarded or destroyed. Their importance lies less in their physical form than in what they symbolize: the application of industrial strength to strategic needs, the value of appropriate technology, and the decisive impact of mass production in modern war. Technical reports from Rechlin and other archives continue to provide insight into these dynamics, helping historians understand how industrial capacity and practical engineering shaped the outcome of the Second World War.